Resolution in thin films, problem number 4. It's a soap bubble. Are you ready to challenge the soap bubble? It's 120 nanometers thick. What color wavelength, so we're really looking for the wavelength, will appear at the center when illuminated by white light? The index of refraction of the bubble film is 1.34. That looks like a problem that we are willing to challenge. So let's do it. Problem 4, let me begin by drawing a nice big soap bubble. Ooh, for me that's probably one of the best circles I have ever produced. So I'm going to relish the moment here. And we have a thickness. Now this is really thin. So there's a thickness here, T is equal to 120 nanometers. 120 nanometers, that's the thickness. In order to illustrate this, I'm going to, it's always good to draw a little sketch. If you don't draw a sketch, you'll get yourself confused. You might anyway. So here is a highly magnified region of this. So we're going to point to this area and consider the details. Well, the details are that n is equal to 1. Outside the bubble is air. The film itself, n is equal to 1.34. And then inside, this is inside the bubble here, n is equal to 1 again. So different speed mediums. And so let's have a beam of light come in. So we have a beam of light that impacts here. And it's going to a slower medium. So, it doesn't really matter for illustrative purposes. It does bend toward the normal a little bit. Okay, like this. And goes into the inside. But there's another reflection here. There's another reflection. And let me just draw it like this. And actually, well, here, let me... Don't like how this picture is coming out. Let me just show it all underneath here. This has a reflection. There's a reflection like that, okay? And so this comes in here. The part that transmits through reflects off. I'm drawing this terribly. Apologize. I'm just going to kind of draw it straight through just so you can see it like this. It bounces like this, and basically you have an eyeball over here that's observing the situation, and this path difference is twice the thickness, right? Okay, so the first thing that we need to consider is what is the relationship that we need to satisfy. What is the relationship? And that is as follows. The need that we have is for constructive interference. We need constructive interference. Therefore, the total path difference, from this beam of light to these two has got to be equal to a wavelength. One wavelength, so that you have constructive interference. If you see the light, it's got to be constructive. But now what we have to consider is, what about any phase changes? Well, we got two possible places where it can happen. The first bounce, right here. And delta phi, is there a delta phi, a change in phase? Well, let's see, you're going from a fast to a slow, so yes, that inverts. In other words, there's a lambda over 2 phase difference from this bounce, because it flips around. Now, down here, we're not worried about what transmits through, but on this bounce, we have a slow to fast, and that does not, in this case, there is no delta phi, all right? Therefore, considering both of these, total delta phi is equal to lambda over 2. Well, we need a total path difference of lambda. We got a phase change of lambda over 2. So what is the path difference got to give us? The 2t, the twice thickness path difference. You could say that's delta L if you want. That has to be lambda over 2. So, and actually, we got to be careful, it's lambda sub n over 2. The wavelength in the medium we're talking about, which is the thin film, with an n of 1.34. So, that means that 4t is equal to lambda sub n. And lambda sub n is equal to lambda in air divided by n. So now, let's solve for lambda. Lambda is equal to n times 4 times the thickness, which is 1.34 times 4 times 120 nanometers, which is equal to 643 nanometers. And that's our answer. We have successfully challenged the soap bubble, and we have conquered it. So keep in mind that when we're talking about finding a wavelength, consider the medium it's in. It's going to be shortened by a factor corresponding to the index of refraction. If it's in air, it doesn't shorten. Obviously, it's kind of the standard. But for any other n, you have to divide the wavelength in air by n. So the wavelength that we see, the end result, is what we see. Right? And so this is what we were solving for. And so the n shows up here. And this particular wavelength is pretty long in visible light, so it's kind of a reddish color in the red-orange range. So there you go. Hope that made sense, and you feel like now you can challenge soap bubble problems. No problem.